Hi, my name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Limited. This video, presented in collaboration with MSC Software, makes up a tutorial from the Apex 101 for Aerospace Applications series and gives an overview of some of the process automation and scripting functionality within MSC Apex. We're using the Harris Hawk Service Pack 2 release to highlight key functionality. In this presentation, we'll go through a number of different automation and scripting techniques, starting with a simple example and progressing to more involved automation. This will be focused on a number of techniques that are typically used in the aerospace analysis lifecycle, but could be applicable to many other industries and types of model. In this presentation, we'll look at a number of worked examples broken down into 4 key stages. So stage number 1, an introduction to Apex automation. So we'll cover some brief slides looking at why would we bother with automation and scripting, some aero-specific examples, Python, API introduction, and the documentation or embedded help within Apex to support scripting and automation. Then we'll move on to a couple of Apex automation examples, so starting with macro recording and automatic execution for a simple example. Then we'll move on to process automation for a thin shell structure process looking at the CAD to mesh activity. Then we'll move on to a parametric analysis for linear buckling solution, and then finally looking at third-party integration for a parametric model build, in this particular case looking at Apex and the integration with Microsoft Excel. Then we'll move on to some more involved scripting examples based on the MSC scripting community. We've got a couple of examples again looking at fastener automation for a large aerospace assembly, and then to the Apex utilities which are available for download to extend toolset functionality. And then finally we'll look at a complete FEA development example, in this case an industrial example using something called Panda FEM, which is a highly evolved toolset for automation of a synchronized global FEM to detailed FEM activity. Okay, so we'll get started with an introduction to Apex automation. So this particular slide looks at why we bother with automation and scripting. So I've broken this down into 4 main areas that I can think of at least. Automation, multiple benefits, so the whole process of FEA is speeded up, so big efficiency gains possible. Error removal, so if you automate a process and ensure that there are no errors in that process, then it removes the potential for manual error introduced. Standardized processes across a company, so people work in a consistent manner. And then democratization for non-experts, so people with less FEA expertise can still generate run-ready models in the fraction of time it would take them previously. Extending functionality, so we can look at additional modeling capabilities. We can add to the solution and post-processing capability from the out-of-the-box functionality, so building on the capability within Apex from the standard solution types. And then we've got integration with third-party toolsets, and we'll look at that in a bit more detail later on. New optimization strategies. So I thought this was an interesting section, in the sense that with a fully parametric model gained through the use of automation and scripting, this potentially opens up new and coupled optimization strategies over traditional approaches. So traditional approaches being topology optimization and size and shape techniques. But if you've got full user control of the overall geometry and many other aspects, loading, material types, that type of thing, then it opens a lot of input in terms of optimization. And then finally, there's a low barrier to entry. The days of complex programming are somewhat behind us, in the sense that it's pretty easy to get started with the MSC Apex Python API development environment. Simple recorded macros can be developed into more complex tools. And then finally, MSC Apex, or the MSC Apex scripting community, is available to share tools, ideas and knowledge, so you're supported with many different aspects of what you're trying to do with automation. Some aerospace specific applications, so again broken down into 4 or so main topics. So automating scripting within the model build, checking and verification process, so CAD to mesh with properties for many structures now is very, very quick within Apex, and it can be speeded up with automation such that a given script can be run on lots of different types of models. We can automate the quality checking against industry standards. Certain things like model connectivity and fastener definition can be automated with huge efficiency gains in there, and we can look at an example. And then we got the potential to automate the global detailed model interface for load scanning for downstream analysis, and again we'll look at the Panda FEM example for that. Automation in terms of analysis and output verification, so we can automate the numerical and fit for purpose checking, and that ties in well with automated reporting. So again we'll see some of the third-party examples, but we can integrate the pre-solve and post stages within the model build into a standardized reporting tool set, so you can drop your images, your tables, your results straight into a Microsoft Word document and standardize against that. And then we've got third-party tool integration, so loads mapping between different tools, for example, wrapper optimization strategy, so again touching on the parametric model definition I spoke on the previous slide, multi-physics integration, and then on we've got many different examples of how this can work in an aerospace environment and many other industries as well. And then just touching on the Python programming language, so MSC Apex is based on the API, rather the application programming interface is based on the Python programming language and tailored specifically for MSC Apex, so we've got many specific functions to support all aspects of FEA. It's intuitive and straightforward, so easy to pick up, lots of free code available all over the net, and free third-party support available, such as integration with Microsoft Excel and Word and many of the tools that people use out there. There are many excellent reference books and dedicated e-learning courses available, and I've just put some images of those examples in the bottom right hand corner. And then finally, a CAE focused language that can be used in many other applications, so gone are the days of learning toolset specific languages with limited lifespan and functionality. Within MSC Apex we have the full Python API documentation, so all functions are supported, or rather referenced in this help documentation, so you can refer back to understand what's going on at all levels. Okay, so we'll look at some Apex automation examples. This one focuses on macro recording and replay. So on the top menu bar, click the red record macro icon, type in a name for the script that we want to generate, or the macro we want to record rather, save the name, input a discrete macro name that we can call specifically from the Apex user interface, and now we're into recording mode. So you can see again on the top menu bar, the pause button has come up if we wanted to pause the process. So we're going to create a simple material, an isotropic material, aluminium, input the elastic modulus, Poisson's ratio and density, the standard way in which you build an isotropic material. Typo in the name, so we're just going to update the name, and once we've created the material we'll press pause on the macro, or stop on the macro rather, so we've now created the Python script. So if we look at the Python file that's been generated, we've got the units, the material name, all the operations that we've just performed, including the name change update, and we're going to go back into the Apex environment, delete the material we created manually, and then simply replay the macro and see how that material can be regenerated in an automatic manner. So a very simple example showing a small number of Python commands. We can see we've recreated the material with the name update, modulus, Poisson's ratio and density in there. So that was recorded and then replayed. So what we're going to do now is invoke a couple of options within the application settings of Apex. So we go into application settings, scripting and customization, and we can specify a couple of checkboxes for post model default. So these are things that we want to happen after or post opening a model. So we specify a script function name and a file location. Pick the Python script, press apply, and we're actually going to use a different script in this example with a slightly longer list of materials. So we've got our function defined, standard Python commands, so creating the material, specifying the material properties. So we've actually got two sets of 2D orthotropic and two sets of isotropic materials. So again, these commands were all generated by recording a macro. So now when we open an Apex database or an Apex session from scratch, those commands are run by default, or that script is run by default, and we'll get a message appear, hopefully, letting us know that the script has completed. Yeah, there we are. There's the message box that's been created. And now if we look in the menu drop down, we've got our two sets of 2D orthotropic and our two sets of isotropic materials, so we can just cycle through those. We've got a cloth and a UD for our composite material, and then an aluminium and a titanium isotropic for use in additional models. So pretty straightforward. Okay, so we'll now look at a second example, this one focused on automated model build. So taking some simple thin wall geometry and recording a macro, similar manner to previous, specify the file location and name the macro we want to create. So we're calling this one mid-surface, or mid-surf rather, 0, 1. We're going to have some iterations on this development, and again specify the macro name if we want to select that from the Apex environment, and then press record. So now we're in recording mode, and again the pause and stop button is shown on the top menu bar. So just going in and mid-surfacing with the auto assign thickness turned on for this simple example. So we've got the mid-surfaces generated, hiding the solids and showing the surface edges. So we've got 3 edges, no congruency between those surfaces at this stage, and then the surface mesh using the default parameters, so 7.5mm element edge length, mesh those surfaces. Again using the defaults, and now moving into extending, so bridging the gap between all the mid surfaces, again using the defaults for this function, middle mouse button to accept, and all of the surface edges have snapped together that lie within that 5mm tolerance for snapping edges. So we're going to auto color the discrete parts that have been generated, so we can see a distinction between those objects within the full assembly. And then moving on to edge type. So this is again using defaults, select the faces, select the edges we want to tie, middle mouse button to accept, and the meshes are now tied together, so we've got node-to-node connection between discrete parts. So stopping the recording and then looking at the macro that's been generated. So bear in mind this is version 1 or 0.1 in the naming convention. We can look through the script. Again, these are standard Python API functions that have been generated. So we've got operations there, render style, get solid, etc, etc. There's a function name given for mid-surfacing. We scroll down, we can see a similar thing again, a function for surface mesh, some function for extending the surfaces, and then finally a function for the edge tie. And again, we can look in the online help to support that if necessary. So we've just moved into a second macro now, based on the first one, and we've just tidied this up a little bit and put some comments in so we can see the code blocks which pertain to the specific functions. Again, just going through that function list again, and see all of the operations that were recorded. And we'll now go and replay this script on some new geometry, or rather the original geometry but re-imported. pick script number 2, the manual update that we just made, and now the script falls over. We've got a problem with the definition. So if we look at the warning message, or the error message rather, we can see the line in which the code has fallen down on. So we can look through the script to that particular point in the code and see that it's falling down on these commands, these ID commands. And effectively what's happening here is the original geometry set, some of the IDs were hard-coded into the macro, and now we've brought in new geometry. Those IDs have been updated and they no longer work for the new geometry. So we can see here in the code that we've got a number of operations which we've commented out. They turn green in the text editor, and what we're going to do is replace these operations with some Python syntax, changing the function type such that it's not reliant on those embedded IDs within the original code. So you can see here we've got a simple definition, so perhaps some basic Python knowledge required, but effectively what we've done is opened up a collection, filled that collection with entity described as targets, which in this case is a list of all the solids within the model. So that's for the mid-surfacing. We've done the same thing again. We've opened a collection called target. We've populated that with all the solid, or rather all the surfaces in the model in this case, and we've meshed those surfaces. And then moving on to surface extension, again using the same surface list. And then finally for edge tie, this is a little bit more involved, but we've got target collections for surface faces and surface edges. So again, populating these using standard Python terminology or logic within the coding definition, such that the embedded IDs which you saw previously have been removed from the code. Now these examples are available if necessary. So effectively what we've done now is updated to script number 4, and we've parameterized the mesh size. So if we replay script number 4 now, the operations are run through, so mid-surfacing, shell meshing, surface extend and edge tie. So now the script has been run successfully, shown on the output screen. We can see the shell thickness, equivalent shell thickness I should say, hide the solids, and we've now got a very nicely controlled model. So for this simple example, worked nicely. So because we've introduced Python logic to effectively determine all of the solid surfaces and edges within the model in an automatic sense, we can now run that very same script on a much more complex model definition or geometry definition. So we've just measured the new model that's come in, and we've changed the mesh size accordingly. So we're setting a mesh parameter of 80 millimeters. Replay the macro, and again all the operations are run through. So mid-surfacing, auto shell thickness, shell meshing, surface extension, and finally the edge tie. And again we've got the message that the script is run successfully, and we're good to go. So what we're trying to highlight here is that once we've got the macro working for a simple definition, we can run it on much more complex assemblies, and provided they lie within existing default values or parameters, but we can set those in the code if required, and we've got a very quick route to getting something that works nicely for us. Okay, so a third example, this time looking at a full analysis, an automated buckling analysis. So we've got a thin shell plate, so turning the 3D thickness, so 3D equivalent shell thickness out of view, and we can look at this simple definition. So we've got the edges are all simply supported, and we've got a compressive load applied on one of the 3 edges, or rather one of the edges I should say. So closing that model just for illustrative purposes, and now we're going to replay a mesh that we recorded, rather a script we recorded earlier and have parameterized. So we've got a number of parameters set within the definition. So we've got panel dimensions, so the X and Y lengths, we've got the number of elements along the shortest edge, shell thickness, and the load magnitude defined. Of course we could do whatever we want with this definition. In terms of model parameterization, a simple example in this case, so we can see panel X, we took the original Python function which had hard-coded X and Y dimensions, and we've replaced that with our variable values for panel X and panel Y. And we've got a couple of other functions in the script which are defined in this manner, certainly for mesh size, that type of thing. So once the script is good to go, we can save the script and replay within a new database, a new Apex database. So the model's stored, press the green button to run the macro, so the model's building, properties defined, loads of boundary conditions defined, and then if you look in the bottom left hand corner, the analysis is running, solving. This is a linear buckling example, so a standard MSC Nastran Sol 105 type approach. So the script is run all the way through to post-processing with no manual input whatsoever, and of course we could couple this with some of the other examples we've looked at previously, mid-surfacing, that type of thing, so we can add complexity and functionality to our scripts. We can see in this example that the buckling factor is less than 1, so the applied load is greater than the critical buckling load, and we can see the first mode there, the simple first mode shape, as it were. So going back, closing this database, and we're going to rerun the script for a new set of parameters. So going back into the script and changing the shell thickness from 5mm to 7.5mm. The units are defined in meters in this particular case. Running through the example again, so model build, load and boundary condition definition, solve, again shown on the bottom left hand corner, and then all the way through to post-processing to understand how the structures behave from a stability perspective. Again, so we've increased the thickness of the panel, and we can now see the buckling factors are greater than 1, in that the applied load is less than the critical buckling factor, so the panel is stable. Fairly trivial example in this case, and probably one that could be addressed by use of a hand calc type method, but illustrative of how Apex can be used, and this slide demonstrates that again, how Apex can be used for parametric definition to make the model build, analysis and post-processing very simple and very quick. Okay, so moving on to a fourth example, a third-party toolset integration. So we've got a Python script here that's been fully parameterized, both in terms of geometry, layout, mass definition, etc. If we look in detail at one of the particular functions in here, we're making use of the XLRD, which is a Python tool available for Excel file reading. So we're incorporating the Excel worksheet in terms of our integrated script definition, so we can specify our parameters. Obviously there's some work in setting this up from a model definition in the first place, but once we've done that and parameterize things, we can run the script, and all the parameters, or the key parameters, are taken from the Excel environment. So we could read write, we can do this with numerous different third-party tools. There's lots of stuff available for Python integration. I mentioned Word, Microsoft Word report file generation, so there's a lot of scope for coupling all these things together to speed things up. So we can see that the parameters have developed a satellite assembly that's shell meshed, edge tied. We've got mass definition in there, what have you. We can see all the masses in the model browser tree. We can, once we've got the model defined, we can repeat the process. So we're going back into the Excel environment on the right hand side, standard worksheet definition, and we're going to change the satellite height from 24 units to 72 units, so triple the height, and save the worksheet or the XLS file and replay the macro, and it pulls in the new parameters accordingly, and again repeats for meshing, edge tie, mass definition, what have you. And we can see this is the second set of parameters used to define that level of geometry. We can now run place an analysis scene and run a normal modes analysis on this structure. We can start to see how the use of Python scripting in terms of parameterizing models, again very quick and easy, but starting to form the basis of a manual or even an automated optimization routine, coupling in some of the different optimization techniques that are out there, evolutionary algorithms, that type of thing. So you've got full model control, perhaps a little bit more powerful when used in the appropriate manner over things like topology optimization and size and shape, but we can see how those changes are washed through in terms of the analysis very quickly. So just looking at some of the mode shapes for the normal modes analysis, we can see fringe plot, animation of deformation, showing what that particular type of structure would do. So again, just a quick slide to illustrate, by changing some of the key parameters we can look at four very different geometry sets and understand their behaviour in terms of the overall structure. Okay, so moving into some further examples, this time based on the MSC Apex scripting community. So this is a series of scripts and tools available and curated by MSC staff and business partners and associations. So there's many tool sets available, and if access is available, then you're welcome to download as many of these tools as required. So the first scripting example from the community that we're going to look at is based on automated fastener generation. So in this particular example we have a shell meshed wing. This has actually been used in one of the previous webinars, so we just run the macro, and if you look closely you'll see that the holes are being defeatured. So as those holes are disappearing, a series of hard points at the node centers, or the hole centers, are being created. Fasteners develop between paired nodes for discrete component pairs, and very quickly run through in terms of the fastener definition. A summary table appears, so we get the output in terms of what's been created, and then the component pairs are named in each connector definition. So within the model browser tree you've got full control in terms of being able to select specific ranges of fasteners for display or manipulation. As you can see here, we've got the rib flange to skin fasteners shown, everything else hidden from view, and if we bring the ribs back in you can see the fasteners and how they're developed in relation to those ribs. So the coordinate frames and properties are all taken care of for a particular area. So huge time savings available in terms of this particular script from an aerospace structure perspective. Okay, so moving on to a second example, and this one looks at a bolted joint. So again, fastener related, but we are now using a script to find CAD geometry that resembles a fastener definition. So in this case, the features that make up those CAD definitions are recognized within the model browser tree, and then we get the summary table to show what's been found. We then convert the CAD representation in 3D into an equivalent 1D fastener with an associated MPC, RB2 or 3 depending on the definition, between components within the joint stack definition. So similar to the original, or the full wing script that we just shown, except that in this case the script is working from CAD geometry that represents the fasteners rather than holes which are within a given tolerance of one another to define where the fasteners sit. So if we look, we can see that the diameter and materials are generated from the underlying CAD representation. Okay, so a second set of scripting examples available, this time looking at nonlinear contact extension. So this effectively shows how Apex can be customized to add additional functionality. In this case, the Sol 400 Nastran nonlinear solution. So we have a macro which builds a 3D hex mesh from the equivalent CAD definition. Hex mesh, or rather solid fastener, required to allow bolt preload to be included. The glued contacts between discrete fasteners within the joint are set up automatically and can be modified, or the resultant script on export will modify these to a full nonlinear solution. So we're just going to change some of the scripting options such that this script is invoked on model export, and we can see some setting files which are included specifically for the Sol 400 nonlinear contact definition. So we export to bulk data file, run the script automatically as we export the model. So just standard model export in this sense, but of course the script will be run automatically. So as we export, the script is invoked. We can do this for, again, Sol 400, which is being run automatically, or Sol 101 if contact is the only nonlinearity within the model. We've automated this particular example to work with third-party toolset, so we're reading in the exported MSC Nastran output into the post-processing environment, and again in an automated fashion, and we're looking at the MSC Nastran HDF results output specifically for contact status output from this nonlinear run. So if we look at the region of interest in the bolted joint, we can see the stress state developed, and more importantly the contact status from the nonlinear solution, both for the bolts and also for the components defined within the stack. So adding functionality to give us this full nonlinear capability. So finally, a much more developed example of some of the scripting available in Apex. This is focused on the panel design analysis, Panda synchronized GFEM DFEM automated toolset that's been developed by MSC Italy. Big thank you to Marco Matola for making this available for the webinar. Unfortunately, this wouldn't be made available via the community scripting, but it's just shown for example. And what we do is effectively automate the global FEM through loads extraction, detailed FEM, and an integration back into the full model development. So we can see here we've got forms developed in Apex to parameterize the overall process, and then a short video which highlights how the some of the capability within Panda FEM. So this is an animation created for marketing purposes. So first of all, we're going to look at a parametric automated fuselage build process. So you can see in the bottom left hand corner some of the scripts that run through. So the tubular section with shells and 1D bar elements defined. So turning the beam display on, we can see how those stiffeners have been generated. And we've got some load application at either end of the structure. Then the Panda FEM script kicks in for the detailed FEM definition, and this effectively rebuilds the GFEM based on detailed panel and stringer definition. You can see here we've got a top hat definition for this particular part of the fuselage that's glued into the structure, and can be run and analysed, post-processed, and then tied back into the global FEM on the fuselage definition. So some potential massive time savings here in terms of the overall process. Obviously a lot of work has gone into this to define both the parameters and the process control, the process flow, but we can see here for fuselage definition we've got model output from a coupled GFEM DFEM perspective. Okay, so to bring this presentation to conclusion, we hope you've seen some interesting use of scripting within the Apex environment, some simple examples to get you started, and then some more developed examples showing the types of thing that can be used within Apex to improve efficiency. If you do want to get involved in anything like this, then don't hesitate to get in touch. evotechce.com. There you'll find a sign up to allow you to join the Evotech Apex mailing list, and here you'll get all updates on anything Apex related, both from a scripting and a general model build perspective. Okay, so before I go, just a great thank you to Stefan Ternelius and Larry Pierce of MSC, who were very helpful with some of the script development and the scripting community demonstrations, and also to Marco Matola of MSC for making the Panda FEM information available for this presentation. Okay, thanks for listening.